I won't mean to, but I probably
Subscribe to my brother. He'll probably subscribe back to you.
That's marvelous. I can't even talk about it right now. I'm emotionally distraught. The rest of this unit is, I mean, I hope you feel like this is good. That's always the goal. I just find that as a teacher, I'm pretty sensitive to where I think students run into difficulties. I don't think math is hard. I think math, like once you get good at basic skills and you understand how to like mess around with X's and move stuff around, math isn't bad, you know. But this kind of math that we have to talk about for the next couple of weeks, it's a little bit awkward. I've said that a couple times now because I'm just trying to make sure that if you feel weird about it, it's not just you. Okay. But we do need to just rip this Band-Aid right off and get going onto the weird stuff. So if you're not done with last night's assignment, just get it done, please. Maybe do a little today, a little tomorrow, something like that, but get it done. So what we have to start talking about today is the answer to a couple of questions. The first question is, what is a function? And there is just no pleasant or easy way to cross this bridge with students learning what math is. I can now say as an adult that I fully understand what a function is, but trying to get you on board, it ain't pretty. So I'm going to write this down and I'm actually going to type it just because I don't feel like writing right this second, but you'll have to write it down. And if you want, we can modify. If as we go, we feel like we want to come up with a better definition, then we'll do that sort of as a team. But anyways, a function is a relation in which there is only one output for each input. And I think that, I mean, within that definition, there's a word that you don't know, right? I mean, you maybe have heard the word in common English, but not in mathematical terms. So what is the new word that we see up there? Yeah, what is a relation? So we'll talk about that after you get this definition down, but um, that's the kind of the new word in that definition is what's a relation. And I don't know how much of what I'm about to say or write down I want you to write down. I'm more just, it's on recording. So anyone watching, I would say just like, hopefully they just kind of absorb it. And if you just wanted to kind of absorb for a few minutes, then you're welcome to. I'm just going to try to give you like a broad stroke idea of what a relation is. Okay. So I'm going to give you another definition. A relation is a set of ordered pairs. And you might say, well, that's not confusing at all. And honestly, once you get it, it's not confusing. You're right. It's just at first trying to show you what it is. So once you get these definitions down, I just want to show you some examples of what a relation means. What is a relation? So let me know, kind of give me a little thumbs up, or I'll watch your pencils. When you're done writing, then I'll know I can scroll up and away. So again, this part, you may not want to even write any, oh, I'm covered in sawdust. You may not want to actually write anything down, just kind of come along for the ride here. This is a relation. It's one ordered pair. If I add another ordered pair to it, like -4, 5, this is still a relation. A relation can have 1 point, it can have 2, it can have 100, it can have 6 billion, it can have infinitely many. A relation is quite literally just a set of ordered pairs. And a relation doesn't just have to look like this. You've seen these before. I know that you, by the time you get to ninth grade, have seen a table before. And if I put some numbers in here like this, like -1, 5, 2, -6, 8, 12, boom, look what I just did. I just made a relation. How many ordered pairs are in my table? There are 3. Okay. This can be a relation, and you're going to see examples of all of these in the coming days. We do these things called mapping diagrams. where our X's go on one side and our Y's go on the other side. And I could put numbers in here like 2, 1, -4. And then in this side, I could do like 10, -6, 8, -4. And then I can draw little arrows like this, like boop, 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 boop. That's a relation. Anytime I represent to you a set of data, a set of points where every X is related to another Y, we call that set of data a relation. Bless you. Can you tell how many ordered pairs are in this relation in the big purple egg? There are 4. Every arrow represents an ordered pair. So like you can see my top arrow goes from 2 to 10. So you would infer from that that the point 2, 10 can be extrapolated from that relation. Can you name another point for me that's in that relation? I see 2 mapping down. Sorry, this is a really ghetto-y arrow. I see 2 mapping down to 8. So 2, 8 is another point or ordered pair. What else do you see?
1, 6.
1 to -6 is a mapping, a point in the relation. What else do you see? -4 to -4. Listen, in the coming days, we're going to talk much, much more about these various representations of relations and what makes a relation a function versus what makes a relation not a function. Listen, bottom line is this: any point or set of points is called a relation. Is that clear? Now, to be a function, there's something in particular that has to be true. And in today's lesson, I'm not going to so much approach it in this perspective, like what's on the board. We're going to approach today's lesson from a strictly graphical perspective. We're going to get this done. This has been a notoriously tough section in the past. So we'll come back and revisit more of this sort of perspective either tomorrow or Monday. But for today, we're going to look at relations, not like I just did them, but on graph. So this is where I think it gets a little bit weird, and I apologize in advance for this, but actually, you know what I'm going to do? I'm going to switch to graph paper. So sorry, I know that you don't have this advantage like I do, but I'm going to use what I have. So here is a graph ready to go. What we're going to approach our relations as today is not just numbers and parentheses and stuff like that. We're actually going to have relations that look like this.
I've seen those before, but I don't know what they are.
This is where it gets ugly. So just do your best to copy it down. And listen, if nothing else, you could just sit and watch the lesson today and just really put on your best listening ears and then maybe go back and watch the video when you have a piece of graph paper, like you're sitting at home and you got some extra time. Once you get this today, you're good. But we today have to talk about domains and ranges and what makes something a function based off of graph. So the first thing that we want to do is give ourselves, and this is a very, very weak definition, but for us, for now, it's going to do just fine. The domain of a relation is the set of inputs. And I will say that in most cases, and this, especially at this level of mathematics, inputs are generally just going to be your X's. The way graphs work, the way functions work is your sideways numbers are like your inputs and your vertical numbers are like your outputs. So when I say to you that the domain is the set of inputs, basically I'm just saying it's the set of all the X's. Does anyone want to guess what the range is? Take a shot.
I'm guessing
It's the set of outputs, also known as the
Y.
Y values. Good. So from this point on, you're going to need to know that domain represents inputs and range represents outputs. Now, here's the where it gets a little bit tricky. If I said to you, forget the red one for a second, if you'd be so kind, like for real, just act like it's not there. Can you do that for me? And let's pretend that the relation was just the purple one. There's no connected dots. There's no continuity to it. There's no flow. How many points do you see in the purple relation? Correct. And you would agree that in the purple relation, the 3 points have names of 1, 2, 3, 4. This point is named -5, 3. Like you know that. Left 5 up 3. What's the name of this purple point down here?
2, 1, -1.
Good. And then what's the name of this fellow up here in the northeast?
5.
Good. Now I'm going to show you real quick how easy it is to come up with domain and range. The domain is the set of x's. So if someone said to me, hey, I need you to write the domain for the purple relation, you do this. You write capital D, and then you make a list. And whenever you make a list of something in math, you should use a curly bracket. That's a set notation. It's like, hey, I'm going to write you a set of numbers. Like I could count these. I could say there are 3. What is the x value of the first furthest point to the left? -5. Correct. What is the x value? The next one we would encounter as we work our way to the right. So we put comma -2. And what is the x value of the point furthest on the right? So we have just, for the first time out of hundreds that we're going to do this together, bless you, we have just written a domain. Easy, right? The domain is quite literally a statement that these are all the x's you're going to find in my relation. The range is going to be written the same way. Curly bracket, make a list. Now, if domain goes from left to right, range should go from low to high. We always want to make lists from small to big. So what's the lowest y value that you see in my purple dots?
-1.
So -1 is my first range value. What is the next y value as I work my way up? And what is the final y value at the top? So this is where I'm going to make a leap. What's nice about the purple points is they are, usually we don't use this word until many years later. Those points are discrete data. They are countable, separate entities from each other. The dots are not connected, are they? There are 3 dots. Here's where the trouble starts. If I said to you that I wanted you to name the domain of the red curve, why is that a problem?
Because there's only 2 points.
So how many points are in that red curve? How many points are in the red curve?
4. Bunch.
How many points are in the red curve? Imagine the biggest number you think you know. Double that. Then raise that to the power of 100. Isn't that still a number? And then multiply that by infinity. Still a number. Are you with me? How many points are on the red graph? Infinitely many. And you might say, no, that's, I see 2. Those are just the endpoints, my friends. Those are just the ends. The thing about points that are connected in a curve like this is you could get the most powerful microscope in the world and zoom in on it times 1 billion. And you're still going to see 2 points with more points between them. And then you're like, no, I'm on a mission. And you go in another 1 billion times. And then you find 2 points that are closer together. And and then you look and go, God dang it, there's still points between them. The connectivity of these, the connection of these makes this red graph what we call continuous. See, the purple graph is discrete. The red graph is continuous. So here's what I want to say. Bless you. We cannot do the domain and the range of the red graph like we did the domain and the range of the purple graph. How many human lifetimes would it take you to name every point on the red graph? In infinitely many human lifetimes, you could spend every second of every day doing nothing but writing the names of points on the red graph, and you, in an infinite number of lifetimes, would not have enough time to write the name of every red point. Which brings me to my point. I need to come up with a different way to name the domain and the range. I need to come up with a way to say to someone that, hey, the domain isn't a number and then a number and then a number. The domain is the set of all numbers from here to here. So let's talk about the red graph. If I say to find the domain of the red graph, we need to use something called an interval. And if you've dozed off because I'm at that point where I'm supposed to stop talking, how silly that I'm still going, try to click back up and wake back in. Got it? You with me? What is the furthest leftness of the red graph? What's the leftmost that it ever goes? This right here is the furthest left that the red graph ever goes. And the X value of that point is -4. Got it? Now what we're going to do is we're going to start an interval at -4. It looks like a parenthesis to you, but trust me, in a couple minutes, it's going to mean a whale of a lot more. Now, by opening an interval, I now say to the world that, okay, my interval has begun. And I'm going to start working my way across on this x-axis from -4, like boom, and I'm going to stop. I'm going to stop on the x-axis the moment that the graph no longer exists. Where is the last x value that I will ever see on the red graph? Right here. Do you agree that this is the furthest right point on the graph? Can you see that little red arrow? I'll make it yellow so you can see it. Do you see that? You have to agree, I'm sorry, but you have to agree that this point right here is the furthest right that the red graph ever goes, correct?
Yeah.
What is the x coordinate of that point? Therefore, my interval goes from -4 to 3. Now, I'm going to trick you. Watch up here for a second. I'm going to not make a parenthesis. I'm going to make a square. Now, today you get to learn about the difference between intervals that have round and square ends. From looking at my graph, what do you think is the difference between the round parenthesis that I put on the left and the square parenthesis that I put on the right?
One's open, one's closed.
One's open and one's closed. In math, by using a rounded end like this one that I'm drawing down here, you're telling people that that point is not in there. It's just a starting point. Got it? And then the square bracket tells people that it does count. That in math is how you express a continuous interval. You literally cannot make a list for these domains because there's no way to count all the numbers. You cannot list them all. Now, let's approach this from a different perspective. Let's do the range. Again, low to high. Can you see with your eyes right now the lowest point on my graph? It is right here, and that has a y value of -1. Therefore, it's game on. Our interval starts at -1, and I use a round bracket because it's exclusive. It's open. It doesn't count. Now, as you scan, imagine like a horizontal laser beam that goes like bzzz, and it scans across, and it stops scanning when it hits what it knows is the highest point this graph will ever achieve. What's the highest y value this graph ever achieves?
5.
It's right here. Can you agree that that's the highest point on my red graph?
Yeah.
And what is the y value of that point? 3.
Oh.
It's up 1, 2, 3. Therefore, the range ceases at 3, square bracket, done. Let's go again. You still with me?
Yeah.
Good.
Saying that.
It's not bad. It's awkward. That's the thing. Yeah. Let's go again. So once again, and you can see why it's kind of hard to take notes on this particular portion because like I have an advantage over you because I have this, this graphing technology, whereas you are trying to probably just put it on notebook paper. So that's difficult. Oopsie. It's continuous, so we know we're going to have to use intervals, right? We can't count this out. We can't go, oh, the domain is there, 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 there. It's impossible with a continuous graph like this. So we think about domain and we start, as of today, we start to understand that domain quite literally means left to right and range quite literally means low to high. Got it? So I ask you, when you look at this graph, and you come at it from the left and you're scanning and you're scanning and you're scanning, where is the first X coordinate on this graph that you will see? So again,
5.
right. So picture that so here's my green line. I'm going to draw you a little laser scanner. So here's my Domain-O-Matic 2400. Are you ready? So I'm going to grab my Domain-O-Matic 2400 scanner and I'm going to start scanning like bzzz, bing, and it sees graph right here. What is the X location of that start? -1, 2, 3, 4, 5, 6. So if we're going to state the domain of this relation, we can say the domain starts at -6. Should I use a square bracket or a round? A square, because the square is our way to tell people that this point is in play. So my domain comes into existence and begins at -6. And now I re-grab my Domain-O-Matic 2400 scanner and I go, and I suddenly realize, oh God, why am I still going?
Because it's not a circle.
It's not because it's continuous, it's because it's endless. Did you happen to notice this arrowhead on the end of this?
Yeah.
What does that mean about that graph? It's never gonna stop. It's gonna go forever and ever and ever and ever and ever and ever to the right. 1,000,000 human lifetimes from now, that stupid graph is still gonna be chugging down there, down and to the right. So when can we say our interval stops?
When there's a circle.
When can we say with this one that our interval stops? Never. We have a name for that. It's called infinity. And infinity always gets a round bracket because of infinity is not obtainable. It's not a number you can get to and say, phew, I made it. Infinities always get round. Is that confusing?
Yes.
It should be. It should be. What'll separate your success or your failure over the next couple of days will be how you approach the confusion. You approach it as, I want to understand this, and you will. Now we're going to talk about the range. And in order to do the range, I have to change now. I can't use my Domain-O-Matic scanner 2400 or whatever I called it. I now have to use my Range-O-Matic scanner. And the Range-O-Matic scanner, he looks horizontally because he's looking at Y values. So if I come at it from the bottom, so here I am, when is the first Y value where I will see the graph? If I'm coming at this from the south, where is the first Y value? Imagine that your horizontal line is scanning and it starts at -infinity. When will it start seeing the graph? Okay, let me phrase my question differently. Sometimes this one makes the difference. How low does this graph go? That was a better question. I should have asked it that way. My graph, my range starts at -infinity. Any infinity that goes in a leftward or downward direction has got to be amended with a negative sign. Now, as my range scanner comes up, you agree that the graph ceases to exist right there, correct? How high is that? What's the Y-ness of that? Therefore, my range ends at 3. Round or square? Nice job, guys. Still with me?
Yeah.
The last thing, because I see that you're getting shifty and I cannot blame you. It's not because you're kids, it's because I'm talking a lot. The last thing I want to explain to you is let's go back to our definition of a function. And you'll remember that a function is a relation in which each input only has one output. So I'm going to show you an example of a graph that is not a function. And you should get this very quickly. If you don't, I'm not saying there's anything wrong with you, but this concept of what a function is on a graph, you should get it almost immediately. So here it comes. Watch red guy. You ready? Red guy's a function.
Never ending, no
It's
beginning.
not because it's never ending. My question to you is this. Could you find me any X location on this graph where there's more than one Y associated with it? So like if Jeff was walking along the X axis and he just said, I'll just stop right here. Thank you very much. How many points on the graph are either above him or below him? One. Try again. It's right there. See? And then let's say that Nash is walking along and he goes the other way on the X axis and he's just piddling around and he stops where the yellow X is. How many points are associated with his location? One, and it's right there. Do you see that? This is a function because every X value has only one Y value that goes with it. Now I'm going to show you an example of something that is not a function. And you might already, if you're really paying attention, you might already know what this is going to look like. I'm going to change this one to, I'm going to stick with red. You ready? This is not a function. And here's why. If Chris goes out for a walk on the X-axis and he stops right here where the green X is, how many points are associated with his location? Three. There's one here, there's one here, and there's one here. Or as Cal so eloquently put it, more than one. Bottom line is this: if a graph ever crosses back over itself, if it ever exists above or below itself, it's not a function. To test this, we use something called the vertical line test. And so think of it just like call it the function scanner or something. And can you see how anywhere in this area right here, how my laser scanner is hitting the graph more than once? You see that?
Yeah.
Okay, I'm going to switch to purple and I'm going to ask you a question. You ready? Purple graph. Function, not a function. It's 100% a function because I ask you this: if I take my yellow scanner, will my yellow line ever see the graph more than once at one time? It passes, we say, the vertical line test. Okay. How about this green one? Function, not a function. Not a function. Look, it fails. Like, boom, right there. It's seeing the graph twice.
This is the graph.
It does. Do you understand? Now, here's the deal. I've eaten up your whole hour, and I am not a teach all hour, ask you to do homework kind of guy. So what I'm going to do is ask you to get started on today's assignment. Okay? It is posted on Canvas, and I do not expect you to get it done. I expect you're going to have some questions. This is all very new. For every problem on the assignment, you're going to see a graph, and you'll be asked to first determine is it or is it not a function, and then you'll be asked to name the domain and the range. And if you get it right away, good on you. That's a huge bridge for us to have crossed today. I'm going to leave the recording alive but paused so that we can maybe go over a couple homework questions when you get there. Let's talk. So the range is, again, the question I ask myself as a kid is, okay, I need to have a cue, something to get me going, a jump start. What do I ask myself when I start the range?
What's the lowest part?
That's what you say. You say, how low does it go? Right? Like the limbo. How low can you go? That's what the range is all about. What is the lowest point on this graph?
-6.
Correct. I don't give a rip how far left or right it is when I'm talking about range. Now, range is just about your verticality. And the lowest point on this graph, you would agree, is right here where I have this red arrow pointing, correct? That's it. And the y-ness of that point right there is -6. So this graph begins its range at -6.
And it goes on.
How high will it eventually go?
Infinity.
To infinity and beyond, right? This is a Buzz Lightyear graph. Like this one goes forever up, 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 up. And so this is a positive infinity, and infinities always get round.
For number 4.
Yep.
How would I do the parentheses?
Well, here's what I'm going to do. I forgot to resume the recording. I mean, it's resumed again now, but since I just did problems 1 and 2, for anyone watching this video, I'm just going to scroll back up to this so that anyone because you can pause YouTube videos, right? So I'm just going to leave these answers up here for just a second, so that someone watching could pause since I forgot to record this part. So good.
Yeah.
Okay. So now let's talk about your number 4.
Like the farthest.
Hold on, before we get there, let's cross this bridge. Is this real quick? Is number 4 a function? No. How far left does it go?
-6.
How far right does it go? So your domain is -6 to 2. How low does it go? How high does it go? So your range is -7 to 5. Done. Left to right, low to high, bro.
But how put the parentheses?
They would all be square because it does make it this far to the left. It does make it this far to the right. It does make it this far up. It does make it this far down.
Okay.
Everything in this case would be a square. Later, dude.
Technically, it is kind of never ending because